All right, this week we're going to start talking about water. Uh, it's kind of important to know water, how much water is in the atmosphere, where it's moving to, uh, how close to saturation the atmosphere is. All these are important in determining clouds and precipitation, two things that all of us want to know about. So I thought I'd just start off by showing you a picture from satellite of water vapor. The whiter indicates more water vapor, the yellow indicates less water vapor. And you would say, oh, well, there should be more water vapor down in the tropics, right? Well, I'm looking at about 700 millibars. So I'm up in the air a little ways. And what I'm looking at, I can show you very quickly over here, zoom in, coming into Texas and Oklahoma and Mexico, there's a plume of air coming all the way down from the Pacific Ocean, the southern Pacific Ocean. This is moisture being transported up into that area from the Pacific Ocean. So if you've got that kind of moisture coming at you, you're probably going to expect a decent amount of rain or some form of precipitation moving into your area. Now, on the other hand, looking further north up over our area, we can see, there's some bluish areas and stuff which are fairly dry. And then there even is a stretch right up in here, quite dry air over top of us. So there's not a lot of moisture up here in our area. Right now, outside my house, it's perfectly sunny. Not a cloud in the sky. You can see some actually on the mountains right here. Little lines of clouds probably that have a little bit of higher moisture content. And you can see some moisture coming in from the west across Illinois, just getting into Indiana, up over Iowa and stuff. That's being pulled in from the Pacific, so there's not a great amount of moisture with it, but there may be enough for some light precip with it. So that's just an example of looking at how moisture moves, and you can see where it is using satellite. Satellite is an excellent tool for this. I wanted to show you another piece, and this would be at the surface. Dew point. We've been plotting dew points on weather maps since you started this course. Well, now we're going to finally learn what they mean. Uh, let's just take, for example, here, Indianapolis, Indiana. Temperature is 22 degrees, dew point is 21. What that says is if I cooled the air, didn't change a thing, just cooled it at Indianapolis 1 more degree down, condensation would occur. It would be totally saturated. So that would be an indication of a very high relative humidity there, maybe a chance of some fog at that level. Now, and I can see the change in dew points. 21 dew point is not a lot of moisture in the air, very low amount. The higher the dew point, the higher the moisture. So down in Texas, for example, 59-degree dew point. The Gulf of Mexico, 68-degree dew point. A lot more moisture down in this area. So let's go through some of this now. Let's start talking a little bit more, shall we say, about humidity and saturation. And we're going to finish up with something called stability. This has caused problems every year. So I'm going to try to do a good job of explaining it. Don't hesitate to ask if you have some questions here. All right. We just showed you in that picture, the very first satellite image I showed you was a plume of water vapor that was coming out from the southeastern corner of the Pacific Ocean. It's an atmospheric river, actually. They occur all over the globe. They're areas with high concentrations of moisture. And when they hit your area, particularly on the west coast, where you have the whole Pacific Ocean for this plume to gather its moisture, there is a lot of precip that can fall there. And you can see how it comes into the west coast, hits the first mountain range that's right along the coast, dumps some rain, but then it hits the higher ones, further, well, closer to our area, and that area really dumps the precipitation on it. And these massive, the longer they're over the same area, more amount of precipitation can occur. We get them on the East Coast. They come up out of the Gulf of Mexico or maybe even the Caribbean Ocean. Sometimes they come in off the Southeast Atlantic. So the total amount of water vapor in the atmosphere is really small and is almost completely confined to the troposphere. So if you were to dump all the moisture, all the water vapor in the atmosphere, and it was equally distributed, you might get 1 inch of water. Well, we get more than that sometimes in rain, and sometimes we get less. So there's an unequal distribution of water in the atmosphere, something that, again, makes forecasting weather kind of interesting. And let's look at where all this water comes from. Here we just got some tables of where a lot of the water is right now. This is what I want to really look at. The oceans, bodies of water, have evaporation. Lots of evaporation comes up into the clouds. That air moves the water vapor to another location, and maybe precipitation is occurring over the ocean from it, or maybe it's waiting till it gets to the land and dumps the precipitation. Actually, there's actually a net deficit of water over the ocean because more water is evaporated over the ocean than actually falls on it. So that means the land actually receives more water to it. However, the land, as you can see here, you have ice caps, water flows down in rivers, comes into ground level, and it goes underground. There are large masses of groundwater storage well underground that eventually flow back into the oceans. So we have a continuous water cycle. Matter of fact, if you look out around my house, I'm right next to the ocean. And there's the James River that comes in and merges with the Chesapeake Bay just north of Norfolk. Where it merges, it's like 6 miles across. Then you have the Chesapeake Bay, which is moving into the ocean. There's actually a bridge on the Chesapeake Bay called the Chesapeake Bay Bridge Tunnel, which is actually 30 miles across at the mouth of the bay there as it's moving into the ocean. If you drive on that bridge, you can't even see the land from some points. Kind of an interesting drive. So you can see all this moisture, all that rain that fell in Western Virginia winds up coming out the James River into the Chesapeake Bay and from there on into the ocean. Susquehanna River in Pennsylvania dumps into the Chesapeake Bay. Now, if you're in West Virginia, you have the Kanawha River. If in Ohio, you have the Ohio River there as well. All that is flowing into the Mississippi, which then flows into the Gulf of Mexico. Again, a large body of water. So you can look and see where these bodies of water, how the water is moving, making these complete water cycles. So, and as part of this, water is the only element in the atmosphere to change phase. So that causes more complications. So here you can see the net loss of water to the ocean and the net gain of water by the land, and the fact that that water from the land flows back into the ocean. Humidity just describes the amount of water vapor in the air, and it really varies by season. I'm going to give you an example here of Oklahoma. Oklahoma raises a lot of wheat in the summertime. And when winter wheat is coming in, it has what they call evapotranspiration. What happens is the moisture that's in the ground gets pulled up into the plants and dispersed, some of it out into the air. Look at dew points in the summer. Before the wheat is harvested, dew points over much of Oklahoma are in the 60s, even low 70s. That's a lot of moisture in the air. However, once the wheat is harvested, and we want to eat that, have bread and all, so we want wheat harvested, that actually drops the amount of moisture in the air significantly in the latter parts of summer in Oklahoma, where the relative humidity goes much lower and the amount dew points drop from the 60s down into the 50s and even some 40s. All because of that amount of evapotranspiration coming out from the plants. Look at Iowa sometimes or in the Midwest where there are a lot of plants and you can just see the dew points in the summertime are quite high. A lot of that is due to the amount of moisture being given out through the plants. Yes, there's other things that move the moisture. The water moves from one location to another, water vapor does. But that's just an example. The vapor pressure, we know, we learned about pressure in the last thing. Every element in the atmosphere has a vapor pressure. Water is no different. Water vapor has a vapor pressure. But when you combine its vapor pressure with all the other vapor pressures in the atmosphere, that's your total atmospheric pressure. So as vapor content increases, vapor pressure increases. But it's no more than 4% of the atmosphere in the lowest kilometer. That's the greatest it's going to get. And that would probably be in something like a hurricane. So we have different ways because we really want to understand water and how much we have in the atmosphere and how it's moving. We have different ways of looking at it. So the mass of water vapor per mass of remaining dry air. So in other words, is mixing ratio. So what I've done is said, okay, I've got a mass, I got a volume of air. I know that this amount is water vapor. Whatever left in that volume of air is dry air. I'm going to use that to calculate the mixing ratio. In other words, how much water vapor per dry air. Now, specific humidity, all I've done is says, hey, I got this whole mass of air. How much water vapor compared to the whole mass of air? That's the only difference. Saturated air is when air can't hold any more water vapor. And air can hold water vapor based on its temperature. The hotter the temperature, the more air can hold water vapor. The colder the temperature, the less air can hold water vapor. You noticed when I said the dew points were in the 60s over the Gulf of Mexico, the temperature was in the 70s. When I looked up at Indianapolis, the temperature was 22, dew point of 21. That's a lot less water vapor. And the reason it's saturated there is because it just can't hold it. So there is an equilibrium. Liquid water becomes vapor at the same rate as the vapor becomes liquid, and that is when saturation is occurring. So we say mixing ratio, we say saturation mixing ratio. Saturated specific humidity. Saturation of absolute humidity. All this is based on temperature and how much water vapor is in the air. So here's a curve of that. You'll notice it's exponential. That as temperatures go up, very quickly the amount of water vapor it can hold rises. Interestingly, there is this little section here, right around where temperatures are below freezing. And we're going to learn that the atmosphere does have supercooled water in it next time. What happens is the supercooled water actually releases water vapor back and forth, has a slightly higher saturation than ice. And that makes a very huge difference later in next chapter. So relative humidity is what you're all very familiar with. You have probably heard somebody tell you, boy, it's a humid day outside. They're probably talking about the relative humidity. In other words, how close we are to saturation. All the relative humidity is that. So at a constant pressure and temperature, relative humidity will vary totally by the amount of vapor pressure in it. However, very rarely does that occur. And interestingly, let's take a summer day, and we could argue this would be a summer day. It could be a winter day as well. But the relative humidity is always going to be highest in the morning typically. Why is that? Well, the temperature is coldest, so it can't hold as much water. So if I have almost no water vapor coming in or advection of water vapor and moisture, then during a given day, relative humidity will rise in the morning till it reaches saturation. It will fall in the afternoon when it gets hotter, and then it will start the whole process back over. You ever wonder why you have fog in the morning in some location? Ah, down in the valleys and the rivers. I used to work at Charleston, West Virginia, at the airport there, as was the weather's office was located at when I worked there. We used to watch the fog rise up out of the Elk River and the Kanawha River right around that airport till it saturated the air. One of the questions we always had every day was just how far up that fog was going to lift. And yet, was it going to go over the airfield, or were we actually going to be above it and would be down over the town? Dew point, as I've told you, is just a measure of moisture when it's cooled, causing dew. Here's the difference in dew points from year around. You can see in the summer they're much, much higher than in the winter. The lower they are in the winter, the less moisture is in the air. When you get below 0 dew points, you have hardly any moisture in the air. And here you can see the precipitable water, highest in the tropical convergence zones, right along the equator. We measure it by using an electronic hygrometer, which is one way of checking how much moisture we have in the air. And I showed you the satellite pictures and satellite water vapor plumes. Here they are as well. So when water vapor air reaches saturation and condensation begins to occur, that is when clouds occur. So if I add water vapor in, maybe clouds will come from that. If I cool the air, maybe clouds will come from that. So if I lifted an air parcel up in the atmosphere, we know the air is going to cool as it's rising. So it can't hold as much water. So eventually it may cool to the point where it causes clouds. However, if I push that same air down where it was a cloud before and now it's sinking that air, well, it's going to warm. Now it's starting to say, hey, I can handle this amount of water vapor. So it dissipates the clouds. Happens on mountain ranges all the time. You'll see where the air is rising on one side of the mountain, you're getting clouds. On the other side, it's sinking, you're getting sunshine. Now we're going to talk about stability. All right, think about a hot air balloon. My easiest example of this is it has air inside it, inside that big balloon. I heat that air up, it becomes warmer than the surrounding air. Warmer than the surrounding air means it's not as dense. We know warm air is less dense than cold air. So what happens if it's not as dense? It begins to rise, and it will rise faster the hotter it is compared to the surrounding air. In the atmosphere, there are parcels of air. I'm going to let you pick your own size you want. They could be from 100 meters across to 1,000 meters across, whatever you want to choose. That parcel of air might be heated by the ground underneath it. It gets warmer than the air in the parcel next to it. So now that air parcel is hotter than the air next to it. It's going to begin to rise. And it's not just rising slowly necessarily. It might rise pretty doggone quickly because it's accelerating upward. The longer that air parcel stays warmer than the surrounding air next to it, the air parcel is going to accelerate faster and faster upwards. So, with that being said, that's all we're talking about on stability, that there's a difference in temperature between air parcels. So here, this is what stable air is like. If the air parcel is colder than the surroundings, that air parcel is going to want to sink. If the air parcel is warmer than the surroundings, it's going to want to rise. At some point in the atmosphere, every air parcel, and it may take it all the way to the stratosphere to do it, will become colder than the air around it. So it will begin to sink. However, major thunderstorms that go all the way to the stratosphere. Once the air reaches the stratosphere is really warming. So what happens is, oh, I have reached a point where I am stable. I'm going to start dropping back. Mountains can push an air parcel up. Cold fronts and warm fronts push air up into the atmosphere and generate these motions. So unstable air now, I'm starting out in the morning sounding. I have air that's relatively cool at the ground. It gets heated. Maybe black asphalt might really heat some air sometimes, or cities heat air just by being the way they are. So that begins to push the air up, lifts it because then it becomes unstable to where it is. But now I'm going to reach a point where I have that moisture in the air condensing. All right, we talked about latent heat released for temperatures. That happens here. When that air gets saturated, latent heat is released into that air parcel. At that point, it will become warmer than the surrounding air and get pushed up even faster. So, as an air parcel starts out dry, maybe it takes a front or a mountain range or something to lift it up. But once it reaches that point of saturation, it may, because of now sending out heat into that air, be warmer than the surrounding air and just keeps on rising faster and faster. That's how we get thunderstorms to develop. All these things impact how that air parcel is going to move. And we know for a fact that if the air is completely dry, air will cool to 9.8 degrees Celsius per 1,000 meter. If the air is wet, and that means it has reached saturation, it's only cooling 6 degrees Celsius per 1,000 meters. So if I have a saturated air particle in one part of the atmosphere and I have next to it a dry air, that saturated air particle, as it's lifted up, is going to cool much slower than the air around it. So it's gradually going to accelerate upwards. So you can actually see on a Stuvie diagram. All a Stuvie diagram is temperature goes in straight up from the x-axis. Altitude or pressure is on the vertical axis. And what we have plotted on here is moisture. And here, this one that's fastest is the dry adiabatic lapse rates. And this one that's a little slower is the moist adiabatic lapse rate. So if I were to plot an air parcel's temperature and it followed the moist adiabatic lapse rate, you'll notice very quickly that it is going to be to the right all the way in warmer. That means it's unstable. And here you can actually see it moving along that track and figuring it out. What causes air to lift? Convection is one, where warmth at the ground heats the air through conduction and begins that air parcel to rise. Maybe it just got a little bit warmer than the surrounding air, but that might be enough. Fronts, warm fronts. We know warm fronts are shallow. They don't lift it as fast, but they do lift the air. Cold fronts, very steep. Orographic. Ever look at all the snowfall that occurs in the West Virginia mountains in the wintertime? That's orographic lift. And these occur, rain showers, shadows actually occur along mountain ranges. That snow that falls in the West Virginia mountains, you ever go on the other side of the mountains? Nothing. That is a rain shadow effect. And winds that are blowing together like sea breezes or lake breezes near Lake Erie can cause showers or thunderstorms. So I hope you got a little bit out of this, and please don't hesitate to ask if you have any questions, especially about stability. I know that can be tough.